We are talking only in terms of geometry, and but how was this geometry established? How did people find that crystals are crystals or crystals are periodic? So, that has an interesting history, and the history begins from the earlier classification of material into crystal and amorphous. Morphing, as you know, changing shape. Morph means shape, amorphous means not having any shape. So, this was based on observing the natural material. Man made material, of course, you can always shape anything into any shape you want by machining and casting or rolling. You have techniques of shaping, but when we say having shape and not having shape, means we are looking at material as found in nature. So, as found in nature, for example, one of the most beautiful things which were found in nature was the snowflakes. So, thing is falling from the sky, no human being is there with his machining or designing technology, and it comes in beautiful hexagonal shapes. You should check images on the net, snowflake images, if you see, beautiful websites are there. At least when I was last checking it, I found a photographer who has dedicated his life. Many photographers in the past also have dedicated, and there is a current photographer, I think Russian, dedicated his life to photographing and uploading snowflake pictures, and beautiful pictures. They will capture your attention. So, obviously they were attractive, and anybody with logical thinking and all also was started to wonder how come they are having that shape, what is the reason behind this nice external shape, and there were other things which were not having shape. So, amorphous and crystal. So, this classification was based on external shape. So, when the question came that why some of, and there are of course snowflakes are beautiful, but as you know other minerals also, for example rock salt. So, rock salt you grow from solution, but it grows as a cube, you are not shaping it as a cube. So, that is in a standard experiment that you take saturated solution of salt, super saturated maybe, and then on a thread you put a seed crystal. So, because of the supersaturation, salt will start depositing on this crystal, on this seed, but when it starts growing you will find that the grown crystal is having nice facet and is a cubical shape. Again, you are not there with hammer and chisel to shape it in a cube, but the growth process itself is making it into a form of a cube. So, these the earlier scientists wondered, some of the greatest mind wondered, and one such great mind was Johannes Kepler. The same Kepler of Kepler's theory of planetary motion. So, he was also wondering. Actually, he was walking back home sometime on a snowfall, and snow was falling on his coat, and some of them he looked carefully and he started wondering. And those days were when there was no DST, CSIR to fund your research, and he was a researcher. So, he has to catch some rich man, noble man who will support such kind of thinking, why snowflake hexagonal. So, he had some baron or some nobleman who was supporting him for his research. So, as a New Year gift to him, he wrote. So, one of one of the most beautiful New Year gift or New Year card you can have is what Johannes Kepler gave to his sponsor or supporter. He gave him a research paper. So, he wrote an article on the hexagonal snowflake. And he gave the theory, his thinking, that why snowflake is hexagonal. And there was the seed of modern crystallography, where he thought that these things which have nice external shape is maybe because of some regular arrangement of internal objects, internal parts. So, that was his theory, that and now what we draw as close packed spheres and all. So, some of the original drawing was in this paper. So, he drew some of these things like packing of spheres. So, spheres are having a spherical shape, they are not triangular, but as you can see in this arrangement, they are giving you a nice external triangular shape. Now, I am writing internal parts because that is what he also wrote, something of that equivalent, because he was writing in Latin. The Latin title was, you will find again on the web if you search. So, atoms were not there. When he was writing, atoms were not discovered. So, he can't say regular arrangement of atoms, some sort of internal parts he thought of. Another great person who came and thought in the same direction was Robert Hooke. Again, Hooke of Hooke's law. He was also interested. Robert Hooke. Now, Robert Hooke was again another intellectual giant. He was interested in many things. So, Hooke's law is only one of his little contributions which we know by his name, but he was an architect. London has a famous, those of you who have visited or will visit London, you can go and see a monument which is called the monument. It is a tower like our Qutub Minar. And who was the architect of that monument? Robert Hooke. Why was the monument made? There was a great fire in London and fire demolished everything. So, then Robert Hooke along with Christopher Wren were charged with rebuilding of London after that devastating fire. So, he was one of the chief town planner and architect of London after that devastation, and as a memory to remember that fire, he also constructed this tower. So, that is called the monument. He was also interested in looking at sun, and he was developing telescope by which you can look at the sun. So, that he called helioscopes, a telescope through which you can look at the sun. All material scientists should do your salutation to Robert Hooke, not for the Hooke's law, but for microscopy. He is the original microscopist. He wrote the first book on microscopy called Micrographia. All hundreds of years ago, 1700s I think, Micrographia. In Micrographia, he also studied some of the crystals, and he found nice external shapes of those crystals. Again he gave a theory similar to Robert Hooke came after Kepler. Again he gave the same theory that the external shapes are because of some internal arrangement. But it was left, because first of all it was not known what is that internal thing which is being arranged and how to find that. None of these things were there. So, his postulate also was regular Then came atoms. When atoms came, atoms were discovered, then these postulates had some more concrete basis, that regular arrangement of internal parts means regular arrangement of atoms. So, then the question came. So, the question was formulated in terms of atoms. That are regular shapes of crystals due to regular arrangement of atoms. But there was no way, no technique to look at regular arrangement. So, the question remained a question. Regularity of arrangement of atoms. Then in 1896, another breakthrough after several years, these were in 1780s or something was happening, and then of course atoms came in the beginning of 20th century, 1900 or so, and just before the beginning of 20th century, in 1896, a new phenomenon was discovered, and that was X-ray. By Ronten. Probably Ohm law there, I am not sure. Why were X-rays called X-ray? X stands for unknown. What was not knowing? Whether they are waves or particles. That was the question. It was discovered, it was found that it is blackening the photographic, that was the accidental discovery. That's another interesting history which you should read. Now all the things are available on net, so you should go and find out. So he was doing an experiment. He was putting photographic film under black paper. As you know, photographic film will get exposed in light, so black paper is used to protect it. He was doing the experiments in dark room. He was using what is called the cathode ray tubes, where the electrons were just like our X-ray tubes, which we used for now our X-ray diffraction equipment. So those equipments had not come, X-ray was not discovered, but he had a metal target on which high energy electrons were hitting, and he had photographic films in his lab, and he found that the photographic films, despite being in the dark room, despite being covered in black paper, are getting exposed. What is exposing it? So when he did careful experiments, then he found that the source of that blackening is coming from his tube. So something is coming from the tube and hitting the photographic plate and is able to penetrate through the black paper. So there is something, some ray, but it was not known, he could not establish. So the name X was given to it. So what was not known, whether it is rays, whether it is waves or particles. That was pre-quantum days, so this question was important. Now of course wave particle duality, so it's photon or it's wave. You may say this question is not important, but those days this question was important, that whether it is waves or particles, because things were either waves or particles. So then came an interesting character called von Laue. He had an interesting insight suddenly. Two different questions. Question 1, are regular shapes of crystals due to regular arrangement of atoms? Question 2, are X-rays waves or particles? Totally unrelated questions. But in his mind these two questions came together, and he had a postulate. He thought optical diffraction was known, so waves diffract through grating. What is grating? Grating is periodic spacing of lines, periodic scatterers. So light, which is waves, through the diffraction grating, one dimensional periodicity, because lines are only translated in one direction, they get diffracted. He had this bright idea that if X-rays are waves and if crystals are periodic arrangement of atoms, so that is also periodic scatterers, but maybe in 3 dimensions. Just like the diffraction grating is periodicity in 1 dimension, the crystal, if it was not known that crystals are periodic, but if crystals are periodic, and it was not known that X-rays are wave, but if X-rays are waves, then these waves can be diffracted by crystal in the same way light waves are diffracted by grating. So, if crystals are periodic, double if 1 and if 2, then so he set up, or his collaborators, he was a theoretician. So, he had experimentalists to help him. So, that then they set up the first X-ray diffraction experiment in the world, where a crystal was obtained, X-ray source was obtained, X-ray source was hit and a photographic plate was kept, a technique which is still called Laue technique of X-ray diffraction. What is diffraction? If you shine some wave on something, you expect the wave to travel through that something. So, that will be a straight through beam, a transmitted beam. If everything is not absorbed, you should get a transmitted beam, maybe weaker than the original because some is absorbed, but you should expect a transmitted beam. However, if that is all you get, then there is no diffraction. Diffraction means that there is some interaction between the material and the wave to generate beams in direction other than the incident beam, other than the transmitted beam. So, if there is beam in a direction other than the transmitted beam, that is a diffracted beam. And they set up this experiment, they were not knowing whether you will find that it is diffracted beam or not. When they set up the experiment, they did find that there was a large patch in the transmitted region, but there were patches away from the transmitted region, showing that the crystal is diffracting. So, it was a very happy experiment, very lucky experiment, for which he got Nobel Prize. Lucky in the sense that diffraction happened. So, diffraction happened, so both the questions were answered in positive, because both conditions were required for diffraction to happen. If diffraction did not happen, then he would not be able to answer any of this question, because maybe X-ray is wave, but crystal is not periodic, that is why you did not get the diffraction, or maybe X-ray is not wave and crystal is periodic, that is why you are not getting diffraction. So, since he got the positive result, both questions got answered and established that crystals are periodic arrangement of atoms. So, that was the historical experiment. In fact, this is considered to be one of the greatest experiments of all time in science. If you Google, you will find it listed somewhere in one of the greatest experiments of all time. And this also provided, this experiment also provided not only answer to the question that crystals are periodic arrangement of atoms, but also in the experimentalist hand it provided a tool called X-ray diffraction, by which to investigate and study those crystal structures. So, the crystal periodicity can now be found by X-ray diffraction. Now, the way I have drawn here, the diffraction pattern is a discrete diffraction pattern. There is a transmitted beam, then there are diffracted beam, let us say. So, since this is how crystallography began, an idea set in people's mind, and if it is not that amorphous matter do not diffract, amorphous matter also diffract. If you put an amorphous thing, glassy thing, that is also diffract, only their diffraction will not be sharp spots. They will scatter also beam, but it will be a hazy scattering in all place instead of sharp diffraction peaks as in the crystal. So, this idea formed that if you see sharp diffraction pattern, it is crystal. If you see a diffuse diffraction pattern, it is amorphous. And we have also seen that crystal is having symmetry. So, the diffraction pattern of crystal shows that symmetry. So, for example, in Laue's experiment, if you have a crystal and suppose the beam is travelling along the fourfold axis, of the crystal, then the pattern which you will get will also have the fourfold axis. So, you will have a straight through beam and other beams will organize, let us say, in a squarish fashion having 90-degree rotational symmetry about that. So, the whole pattern will also have the fourfold axis. So, people were happy. Crystals give a sharp diffraction pattern, and from the symmetry of the sharp diffraction pattern you can find the symmetry of the crystal. This is where the problem began, that in 1984 when Shetman did his experiment, and he was not doing X-ray diffraction, but electron diffraction. In transmission electron microscope, TEM. What he found, he was working with aluminum manganese alloy and he was looking at the diffraction pattern. What he found, that he is getting sharp diffraction pattern. Which is indicating that it is crystal. But the symmetry of the sharp diffraction pattern was tenfold, and in Shetman's time this crystallographic restriction theorem which I taught you was well established, that no crystal can have tenfold symmetry, and only crystals can give you sharp diffraction. Now, we are just stuck with a diffraction pattern which is sharp, indicating crystal, but it is also having 10 spots regularly arranged, tenfold symmetry. So, in his notebook just he wrote tenfold question mark, and I started wondering about it. Often, see, now as a PhD scholars, you should be very, very careful in if your results are not matching with theory. So, this is an example of a result not matching with theory. He could have easily thrown this in a bin, कुछ गड़बड़ हुआ भाई, ये तो लोग हंसेंगे, मैं बोलूँगा मुझे 10-fold crystal मिल गया. Everybody will say you have look at your experiment, repeat it or do something. So, he repeated the experiment, it was repeatable, he was getting this 10-fold symmetry. So, the issue was, so finally what got established, that this logic that only crystal can give you sharp diffraction had to be revised, that and a new class of material was found. So, crystal gives you sharp diffraction pattern, amorphous gives you diffuse diffraction, but now between crystal and amorphous came quasi-crystal, which also can give you sharp diffraction pattern. And why quasi? Because they are not periodic. Doesn't not periodic means random? No, amorphous is random, no order, but you can have order which is not periodic, and what was found that these quasi-crystals have quasi-periodic order. Let me just give you a one dimensional example of quasi-periodic order, which is very well known in this quasi-crystal literature. 3D is more challenging. So, let us start with what is called a Fibonacci sequence. Fibonacci studied rabbits. He said that and he made a model that let us say that there is a baby rabbit, in a month's time it will become adult, and then adult will give rise to a baby. Then in the next month again the adult will give rise to a baby, and baby will become adult. So, you carry on, A goes to AB. If you do not like rabbit or adult or baby, you must already be getting confusion that how a single adult can give a baby or things like that. So, you just can think of a transformation that B transforms to A and A transforms to A and B, a pair. So, B becomes A, in each generation B becomes A and A becomes AB. If you see the number of rabbits or number of these elements, that is what in number theory is known as Fibonacci number. So, you have 1, 1, 2, 3, 5. So, every number is sum of the two previous numbers. Now, how does it relate to the quasi-periodicity? In quasi-periodicity you can think of that you have by B you think of a small segment, and by A you think of a large segment. So, you have two length scales. A periodic arrangement of points has one length scale, A. So, or let us say S. So, this is a periodic set of points, all points separated by S. But now, I start making my points separated according to this Fibonacci sequence. So, wherever I get A, I put a long, and wherever I get B, I put short. So, long, short, long, short, long, long, short, long, long, short. Think of repeating this process. I have repeated only 5 times. Repeating this process to longer and longer iterations, more and more iterations. You will get a sequence of long and short segments. Is it periodic? It is not periodic. You are already seeing long, short, long, long, short. Okay. If you had LS, 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 that was also periodic, or if you had LLS, 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 that was periodic. But in this process, you will never, in this Fibonacci process, you are never assured to have periodicity. You do not have periodicity, but is it random? You are getting it by a very systematic mathematical process. So, even in nth iteration, you know that this is what you will get. Whereas, if I start throwing L and S really randomly by tossing the coin, that head means L and tail means S, then I will get a random sequence of L and S. So, that will be a one dimensional amorphous sequence of points if L and S are thrown randomly. If L and S are thrown in a Fibonacci sequence, then it is neither random nor periodic, and this is what gives you the so called quasi periodic So, quasi-crystal is a 3-dimensional generalization of this thing. So, instead of a single unit cell, there also they have 2 unit cells and 2 unit cells packed together, and but their packing is not totally periodic, but still they have some, but it is not totally random also, that you do not have any kind of unit cell. You do have 2 unit cells which are arranged in some particular quasi periodic fashion. So, since they are not restricted now by translational symmetry, so our crystallographic restriction theorem that derived from periodicity. So, these quasi crystals are free from the restriction imposed by periodicity. That is why they can have symmetries which are not allowed for crystals. In fact, what Setman saw in the diffraction pattern as 10-fold axis was really a 5-fold axis, and the aluminum manganese quasi-crystal was shown to have icosahedral symmetry.